Welcome to this video on reversible versus irreversible processes. In this video, as the title hopefully suggests, we're going to be defining what a reversible and an irreversible process is. But I think what's more important than just defining those two arbitrary words is actually figuring out, why do we even care? What is the point of knowing what a reversible and an irreversible process is? And I think the main idea here to always step back and think about is this term efficiency. When we think about efficiency, we're basically saying that we want to be able to get the most work out by putting the least amount of energy in. If we multiply that by 100, we would get the percent efficiency of a particular engine or any process. So when you get a little bit lost in the details here, take a step back and just think about this. We're trying to get the most work out by the least input. That would get us as close to being 100% efficient as possible. This would allow us to use less energy to achieve the same goals. So let's talk about a couple assumptions that are going to be extremely important in understanding these two words. Because these words are very abstract, they can become a little bit confusing if we aren't all operating from the same assumptions. So just a reminder that a process is when I change a system from state A to state B. And this can occur in two general categories of heat exchange or work done. And keep in mind that these can both occur at the same time. Now what we did was we looked at a couple of different processes. We looked at an isobaric process in which there was no change in pressure, heat was exchanged, work was done, and of course the internal energy of the system would have to change as well because there would be a temperature change. An isochoric process, or an isochoric change in a system, is one in which there is no volume change. This means that there can be heat exchanged, there can be a change in internal energy, but there is not going to be any work done during the process from A to B. An isothermal process that we looked at quite extensively was one in which there was no change in temperature. This meant that automatically there would be no change in internal energy of the system from state A to state B, but that work was done and heat would have to be exchanged in the process of that occurring. The last one that we've looked at was the adiabatic process, and this was defined by the fact that pressure, volume, and temperature could all change, but that there was no heat exchange between the system and its surroundings. In this case, again, work could be done and internal energy would have to be changed of the system, but not because of an exchange of heat between the system and its surroundings. Now, why I'm reviewing all four of these very quickly is because we're going to be looking at a pressure-volume diagram. And something that confused me when I first learned about reversible versus irreversible processes was that I assumed I would have to be able to tell if a process was reversible or irreversible by looking at a PV diagram. And the truth is, you cannot tell if a process is reversible or irreversible from a PV diagram without additional information. So let's take a look at that. So over here on my PV diagram, I have a gas that's currently at state A, and the gas is inside this piston, is inside this cylinder with a piston that's currently located here that I'm going to call at position Y sub A. Now what's going to happen is it's going to expand, and I'm going to say it's going to expand isothermally to state B, where we will have the same amount of gas still in the system, but it's going to have a lower pressure. As you can see, that value on the axes, if I line it up with the new point that's been graphed, that there has definitely been a pressure drop. So PA to PB shows that there has been a pressure drop. But at the same time as that pressure drop occurred, we had an expansion from VA to VB. So what I can say here is now that the piston is at a height of YB. So over the change from state A to state B, what I would say is that there was a height change, and that height change is equal to YB minus YA. Now, I could calculate the amount of work done during this expansion from A to B, and we're going to talk about that in a little bit. Now, we know that if this is an isothermal expansion, that means that heat had to flow into the system in order for this system to increase without a temperature change. So keep in mind that the temperature at A is equal to the temperature at B. Now back to the point of this video, is this process, this isothermal process from A to B, reversible or irreversible? And the truth is, there is no way to tell without more information. So what I'm going to do here is take you through a series of little thought experiments to help us define what would this look like if this was an isothermal reversible process or an isothermal irreversible process. And basically what we're going to say in the difference between the isothermal reversible process to the isothermal irreversible process is whether you can go back to state A without having lost a lot of energy in the process. So in other words, can I go from state A to state B and back again without having lost anything in the process? That would be considered a reversible process. If I go from state A to state B and try to go back to state A, I would have lost something in the process, and that would be considered irreversible. The truth of the matter is that a reversible process where we can get a gas back to its original state without any loss or excess energy, that's going to be considered very much ideal. An irreversible process is the lot more realistic one. Now, as an engineer, your goal would be to make the process as ideal as possible because that could make it 100% efficient. Now, we know that that's not going to be possible just from all the science you've learned before. We always know that there's always a cost involved. But we can always try to come up with a way that makes something more ideal. So for us, we are going to define ideal as reversible and real as irreversible. So when we go through this little series of thought experiments here, that's what I want you to think about is, how is this an ideal process versus how is this actually realistic? And what that main distinguishing factor is going to be between the two is what I'm going to refer to as a loss of usable energy. A loss of usable energy is what is going to determine whether we have an irreversible process or a reversible process. So I have my thought experiments set up here, and that's what's most important to remember in this process is this is a thought experiment. In other words, it's probably not possible to actually carry out this experiment in a way that is completely measurable, but it's going to help us theoretically think about what's happening. So in this cylinder, I have it here in state A and then again in state B, and I've laid the cylinders side by side so that we can track this height change and make comparisons. The first thing I'm going to note is that I have a brick sitting on top of the piston. So the pressure inside here, the pressure at state A, is going to be what is exerting a force on this piston to hold this whole system at what we are going to refer to as equilibrium. Now, when I remove the brick, so I'll go ahead and actually lift the brick out of here and put it sideways, I guess, just right where it was originally. So really what I should think about is not necessarily lifting the brick over the sides, but actually just sliding it to the side like this. Now what's going to happen is that, of course, this pressure is going to push the piston, and if they're not at equilibrium outside here versus inside here, that the piston will raise to another point where it will reach a state of equilibrium again. Now, in doing this, what has happened is work was done. We had work done as there was a volume change. And what you can say now is to get the piston back to state A, what you're going to have to do is take your brick, raise it up, and slide it back on to the piston. And this would, of course, push the gas back down again, and we'd eventually be back to point A. Now, what we want to think about when we're thinking about a reversible process and this brick example is that we're trying to show that the work it would take to raise the brick back up to this height over here against its weight would take some effort. So here let's calculate how much work it would take to raise the brick up to the purple line and put it back on the piston to bring it back to this state. Well, we showed here that we had the high change of YB minus YA, and we have to exert at least the force of the weight of the brick. So work is equal to force times displacement. The force is mg, the displacement is going to be delta y, and we can see that that's how much work it's going to take to get the system back to its original state. Now, we're never going to be putting bricks on pistons in a real engine, so why are we using this example of a brick being the determining factor that changes the system? Well, we need something visual in our thought experiment to help us understand what's going to be an ideal reversible process that's efficient versus an irreversible process. Well, we're using the work required to raise the brick and put it back as an visualization of the loss of the usable energy of the system. So here's the way that we want to think about it. The work required to put the brick back on to the piston and push it back down to its original state, this is going to be equivalent to the amount of energy lost during the process. So keep this in mind, that when we talk about the amount of energy lost during the process of changing the system from state B back to state A, or we could say as the state changes from A to B, we are looking at that in the form of a brick being removed and then put back on. Now the story goes that in order to make this a little bit more efficient, what we're going to do is we're actually going to chop the brick in half. Now what's going to happen is that when we have the original two pieces of brick back over here on our piston, we're going to remove them in two parts. So let's take a look at that. So here I have the drawing where we have the piston halfway because we're going to remove half the brick. So what I'm going to do here is draw in just half the brick still on the piston. Now the first half of the brick was slid over here onto the side, and the second half of the brick is still on there. Now when I slide, I'm going to do it again, take the second half of the brick off. The brick is going to be even closer to where the final position of the piston is. So I have state A, I'm going to call this state I for intermediate, and then going to state B. Now what I've done is I've taken half the brick off. It ends up being at this height, YA. The other half, now it stops in the middle, I'm going to call at YI. And I'll slide the next half off at YI and we'll be at YB. Now if I calculate the amount of work done in order to put the pieces of brick back on, I've got less delta Y part of my effort required to put the brick back on. So I'm only raising it now half of YA, YB distance, and I'm only raising half of the weight. And then I'm going to do the other part again. So in each of these little changes, what I'm saying is less loss of energy has occurred because I've done the process a little bit more incrementally. Now remember, the whole idea of measuring how much work it takes to put the brick back onto the piston is trying to visualize the energy lost during the process. Now if I did this again and I broke the brick into, say, 4 parts, now I would have more intermediate steps whereby I'm taking just little pieces of the brick off, and I could keep going to infinity where I would have an infinite number of little steps in between here where little pieces of the brick were removed as I got to state B. Now this seems, again, to be a very sort of arbitrary and weird process. Why do we even care? Well, the point that this thought experiment is trying to get at is that you can have a reversible isothermal process if you make infinitely small little changes as you go from state A to state B. So if you go really, really slowly, you can get from state A to state B without very much energy loss during each little change. So basically what we're going to say here is that the more little equilibrium states we have in between going from state A to state B, the more efficiency we're going to have. So the less energy loss we're going to have in the entire process. So I'll say that again. The more little equilibrium states we have on our way, which here we have as intermediate, so the more intermediate equilibrium spots we have between state A and state B, the less energy loss there is, and the more reversible the process is defined to be. So you can think about if you take the brick off and it expands straight up to this point over here, you're going to have quite a lot of energy loss. But if you do this in very, very small increments, we're going to have less and less energy loss as we go to our next state point. A very important thing is that you cannot tell on the PV diagram unless somebody tells you that this is occurring reversibly or irreversibly. So irreversibly means that I have energy loss during the process. Reversibility means that I have no energy loss. Now, you can think about the fact that on the way of moving this, that as these parts are moving, as the piston's going up and down, and it's happening very fast, we're going to be losing all kinds of energy. The brick example is just a visualization of the energy loss that's going to occur due to friction and due to heat being lost from the system on the way to achieving the amount of work being done. And so it's not possible to have no complete energy loss. You can get there by going as slowly as you possibly can, but then you'd be better off walking rather than using the engine of your car, because you'd have to go so slowly to prevent any sort of excess energy loss that here again is being visually depicted by the brick being broken up, that it really wouldn't be practical. So what you're doing as an engineer, if you think about this, is you are trying to make a more efficient engine, and the way you do that is by making each of the processes in the engine more reversible but still practical. So basically what we need to do is find ways to expand and compress the gas in the cylinder with as little energy loss as possible to make the overall process as efficient as possible. And it turns out that a mathematician, physicist, and great thinker, Sadi Carnot, came up with the theoretically most reversible engine or most efficient engine process in what is now known as the Carnot cycle, which we'll take a look at in the next video.